All right, so what I want to do in this second part is go over some of the model classes used in high dimensions and say why or how they're implemented and whether they're successful. Is there theory to back up their usage? Okay, so that's sort of the main idea of the second part of the talk. But before I do that, I want to say that there's this disjointness between approximation theory and numerical approximation. Because in approximation theory, as you saw, we assume we have full knowledge of the function. I mean, I never said in the first part of the talk, do I have the information I need about the function to implement or find such an approximation? Now I want to mention that part. So there are two, typically in numerical settings, there are two formulations that you can be confronted with in high dimensions. That is, okay, you have this target function you're trying to find, right? You're trying to approximate. You're trying to make it simpler by some approximation scheme. And then I can say to you, well, in what sense do you know this function? I mean, how do you have information about this function? And there are two ways. One way is you could have queries. That is, I tell you that if you ask me for the value of this function at any point, I'll tell it to you. You ask me. Oh, hey, here it is, right? These are called query algorithms. So suppose I have this high-dimensional function, and I give you the right to ask me questions about it. For example, with value at a point, or more generally, apply a linear functional to it, like an integral, or ask for its Fourier coefficient, and that would be an integral. You could do it here. So that's a query algorithm, but you have to pay for these queries. So you have a budget of how many queries you can ask, or some dollar budget. Every query costs $1. And you're not rich, are you? Are you rich? No. So $100 is a lot. So you have a query budget. And now the question is, what should your approximation scheme be? What is the model class? And where should you query? Given a model class, where should you ask the questions? I'll mostly talk about the case where the queries are what we call standard information. They're the values of the function at a point. Do I have it on there? Maybe it's on the next slide. Okay, another setting, and one that's very common these days, right, with all this learning stuff, is that you're given data. You didn't have the option of saying, well, I want the value at this point and that point. No, you're given data. That's it. Somebody presented data. We call this data assimilation. You're given data. That's it. Once and for all, you're given the data. Or maybe it comes in a stream, but in any case, you have data. And you cannot ask where, for values at other points. You're only given the data points. How well can you approximate now? Now that has to cost you some, right? If I prove some theorem that this model class, if f is in this model class, I can really approximate it well. But now I'm in a situation where I have data. You could give me real lousy data, right? And I have to pay for it.
So are you meaning that for your data, again, is information is still linear functionals applied to f, except that you don't get to choose them?
I don't get to choose them. And but I'm going to mainly concentrate on the case where they're the values of the function at points, which is called He knows all this. Standard information, right, in the IBC community. I'm going to mainly talk about that, but the general problem of data assimilation is they could be linear functionals. Like in your parametric PDEs, you have this dictionary and you're trying to construct a dictionary. But anyway, okay, so this is the information I have. So the point here of this slide is that be aware that it's not just approximation, it also depends on what information you're given in a numerical scenario about the function f. If you're only given data, if I tell you I have a function on 0, 1, and I want you to reconstruct this, and I tell you some model class, and it's in the model class, but I give you data that's always the values near 0 and never near 1, you're not going to do very well, right? How are you going to resolve it near 1? It's impossible. So that has to come into the picture. Okay. So query algorithms. In a query algorithm, you ask for the values. Here I have the standard information. When you ask for only point values, when the information is just point values, that's called standard information. In the general formulation, they could be linear functionals. You could ask for any linear functionals. Now, so the problem would be, suppose you had a model class, you're in high dimension, and I say you have a budget, you can ask n questions. What questions should you ask in order to resolve, to find an approximation to this function? So let's say I'm in R100, function of 100 variables. And I say you can ask for the value of this function at a point. Any point you want. And you ask and I give you the answer. I say 0. It's 0 at that point. And you say, well, how about this point? 0. And I keep saying 0. And that's the information you have about the function. How well can you resolve it? Did you ask the values at the correct point or not? So you should anticipate you're going to get 0 every time from me. And now the question is, of course, knowing it's 0, let's say you have a function in lip1 and in one variable, right? If you have a function here, Lipschitz1, which means that as you move, right, as you move h, you rise at or fall at most h, right? Now you know that if you spread out these queries, you can resolve. If you ask n queries at equally spaced points, n equally spaced points, you'll resolve this function to accuracy 1 over n. But now let's think high dimension. If I'm in high dimension, R100, how many quadrants are there? What do they call them? Entants in R100. There are 2 to the 100 entants. So you start asking questions. I say, I give you 1,000,000 questions. You're going to get nowhere, right? Unless your model class has some special properties that allow you to do it. This is the curse of dimensionality. You need the model class, the functions. You have to have extra information about these functions. Okay, but there's a general theory that tells you where what the benchmark performance is. If you're talking about query algorithms, it's called the Galfond width. I talked to somebody in the coffee break. And they, where is he? What's your name? He said, well, I followed most of this stuff, but when it came to this entropy widths and all that, so, well, yeah, that's true. You just copy that name down and you Google it later, right? If you find some concept here you didn't understand when I presented it, but
well, just that you're going to get the slides, right?
Yeah, they can get the slides.
So we'll put up the slides.
But the point is, I mean, we all face this when we hear talks. We hear something and it sounds important and interesting, but he's on to the next topic before we digest it. But the important thing is, okay, we heard those words and we know it's connected with this, and so later when we're trying to optimize something, we say, yeah, but there's this idea of Galfond width that optimally tell you where to query or what the optimal performance of query algorithms is, and then you can look it up online. I mean, I use Google all the time now. When I first started collaborating with engineers, they were 20 years ahead of me, you know. You would say a word and do you mean this? You know, Hilbert's 13th problem, whatever. Okay, so Galfond widths tell you the optimal recovery. It's like Kolmogorov widths. Huh?
Question. How is it
connected to information theory. For example, in Bayesian optimization, where you query based on the information that you get.
So
You want to optimize that, right?
So in Bayesian, are you given random information, or you actually can direct
So
them?
you can direct where to query.
Yeah.
And you want to query where you get
Yeah.
information.
Right.
I don't
So,
understand how it's connected.
okay, so this is how it's connected. So it's like this game. So you say to your child, you say, I have a number between 1 and 100. Guess the number. They say 17. You say, no, this is not the way to do it. The way to do it is to ask, is the number between 1 and 50 or 50 and 100? Ask a better question than, is it 17, right? So this is the query. He asked the question. So they say, is it between 1 and 100? Or 1 and 50? And you say, yes. Is it between 1 and 25? Yes. 17! Right. No. So the idea here is that we always have, when we start querying, we have unknown territory. We have territory where we don't know the answer, but the model class puts restrictions that says in this territory, the function can't change too much, or maybe it can. You ask a question where it can change a lot, and you try to divide and conquer the territory. This is basically the idea.
Maybe what you have in mind, I think, is for example, Gaussian process.
Yes, exactly.
Interpolation. So in that case, there is no. I think it's just what you said, but the model class is replaced by which is a probabilistic object. I think the
By probability distribution?
By a process. Okay, so you can think of it as the analogy.
But in GP, we can get the information about uncertainty that we can, like, for example, query where the uncertainty is highest. There we can, like...
Yeah, but then can you, for example, it gets interesting to ask the same question, can you sort of quantify how well you can do with this amount of queries? I mean, can you for sure tell? So it depends, then I guess that depends
On the model class.
process on your, the model class is replaced by the assumptions on your process. What are the covariance functions and things like that. So this is
So Puya, when you do that in Bayesian optimization, so you are assuming that you know the kind of process behind it?
Right.
And if that's okay. What Abel said, that's the analog to that K.
that's the analog, but
That's the information.
hope for result in that case, probabilistic nature.
Yeah, so I'm in a deterministic world here. I'm not in a stochastic world. These concepts all have analogs in stochastic world. And then there's the merging of stochastic with deterministic, in a sense that the deterministic, if you take this stochastic formulation and you look at a realization, you get a deterministic object. And what's the probability that, if you look at a deterministic object, you can say, okay, I'll look in with high probability it's in this class K, this deterministic class. I mean, but we don't have time to do all that now, okay? But that's sort of the... Okay, so let's say we're in a situation where we have a model class. We're pretty convinced this is a good model class for our problem. And we want to, now we have a function f and we want to find it. And we're allowed to query, what should we do? That's going to be something I'm interested in. As I said to you, query in high dimension is very questionable, right? Because 2 to the 100 quadrants, you can only get 1 point. I mean, it seems like impossible, right? Function of 100 variables. What are the common strategies? Well, again, it's going to depend on putting restrictions on your target function. By saying it's in a model class, that means it's not as complicated, or there are not as many possibilities as you originally thought. So some strategies, Monte Carlo, for high-dimensional integration. You hear that all the time. But even Monte Carlo, I mean, if you want high performance of Monte Carlo, you're going to need some assumption on the function you're integrating, right? I mean, you need some restriction on, as a function of 100 variables, some properties that will allow you to sample and resolve it. You can always think that when you sample, you're going to get 0 as the answer, and then you have to be able to say, okay, if it's 0 at all these places, it's close to 0 everywhere. The model class should impose that. Okay, compressed sensing is based on that. Albert is going to talk, right, about this in his lectures, and his idea is that you're going to choose a probability distribution for which you're going to do the sampling random with respect to that distribution. That should be merged with the model class, or that choice is an important choice, what probability distribution. So you'll see that in his talk. In deterministic settings, the typical high-dimensional querying are hashing. Do you know hashing? Hashing is like this, what I just told you with these asking questions. You got a number between 1 and 100. You ask a question that will eliminate half of the possibilities, and you now have the remaining half. And then the next question cuts in half again. Hashing is sort of dividing in two. With every query, you're sort of eliminating half of the territory or half of the possibilities. Discrepancy theory, these are algebraically, we'll say something about this later. Cohen-Macaulay theory, commutative algebra, not this Cohen, a different Cohen. He hasn't done everything. Sometimes it looks like it, but he hasn't. Okay. And data assimilation, again, we don't, I'm just going to tell you that the main strokes of data assimilation. We don't get to choose where we query. We're given data. So we're given m pieces of data, numbers. What are those numbers? They're the value of a linear functional applied to our f. Maybe it's just the value of f at a point, right? Or maybe it's the integral over some small region near a point. That's more likely. So this we don't control. We're given that. We have no control over it. That's all the information we have about f. We have this data, and we have that it's in the model class K. That's it. What's the best strategy? What's the best thing to do? How do you recover f in this case? And what's the optimal error you can achieve? This subject is called optimal recovery. So if you're ever confronted with a problem like that, Google optimal recovery. Given information, given a model class, it tells you the best you can hope to, the best accuracy you can recover. Okay? So what I'm trying to say now is that there are tools that we have developed in approximation theory and related areas of functional analysis that measure performance and measure optimal performance. They can be useful for you to decide in your given application how well you can do. You should check the model class, see if it breaks the curse of dimensionality. You should understand whether you're in a situation of querying or data assimilation, your given data. And then you should look up the appropriate concept. If you're in the process of data assimilation, look up the subject of optimal recovery. It'll tell you the best you can do. Usually you'll be disappointed because your model class isn't going to be one where they've done the optimal recovery for that model class. Why? Because you're clever. You found a great model class in high dimensions nobody thought about. But then you will see techniques for trying to estimate the optimal recovery. Okay. I skipped that. Okay, now I want to give you some examples of model classes and approximation techniques and querying techniques where we feel we're doing a pretty good job. So these are scenarios where if the target function f falls in these model classes, then we would say we are handling the high dimensionality very well. Okay, here's the first one. So I'm going to go through this maybe faster than I should because I want to save some time at the end to say something about deep learning. Okay, so the first model class, this is rather a toy example, or rather too strong of an assumption, you would say, but it would tell you an idea and then tell you that we can generalize this so it's not so restrictive. So think that you have a function of a lot of variables, d, continuous function on a big cube, 100-dimensional cube. Okay? And you're saying, okay, that I know my function f is such a function, and I want to, it's a high-dimensional function, and I want to recover it or approximate it. What would be a possible model class that would allow me to do it? I mentioned to you that the idea that if it actually only depended on a few of these variables, you may not know which ones. Let's say you have a function of 100 variables, but only 3 are really important. You don't know which 3. Then this is going to tell you what you should do. Okay, so what's the bottom line? The first thing is, you could say, let's say if we were given a problem to query. I mean, we were allowed to query. So we're given such a function. We're trying to drill for oil. The flow depends on 100 parameters. And we get to say, drill here. We get to drill here. And then we have to then say, after all this, okay, there's oil here. That's our problem. Okay? So the question is where to query. So if you have a function, 100 variables, only 3 are important. I don't know which 3. How should you query? Where should you ask for information? The answer is to do hashing here. Hashing queries. Now let me, so I don't have time to get into details, but you'll register in your mind if I have a function of a lot of variables, but only a few are important, I'm going to do something hashing. So hashing in this context is very similar to compressed sensing. You see, you would like to find out the 3 variables that the function really depends on. You don't know which 3. So you ask the value at a point. Then you ask the value at another point. And you can see between that point and that point, did it change? Now, a lot of times it won't change because it only depends on 3 variables. Or the change is very little if it depends weakly on all other variables. So you want to ask a question that touches all the variables. You want to ask the value at a point that touches all the variables, and at the next point that changes a lot of the variables. So you can see, because, and then if you see that there has been a change, then you know that the variables you changed, that set of variables, contain some of the 3 variables you're looking for. Then you ask the next question, etc. So you always change half of the variables. Keep half of them fixed, change half of them. If you see a change and you know one of the variables that you changed is an active variable. That's hashing. It's like dividing in 2 the possibilities. Okay, so that's the strategy. Then you'll determine the change variables. And okay, so we're not going to get into the details of it, but that's the general idea.
What if 2 of them?
Huh?
What if only 2 out of 3 are on the half of?
Yeah, you'll only determine them, and then you have to return back. But you also have the problem that the function may not change on those 2 values you have, but some other 2 values it changed. So to develop exactly what the theorem is, I don't want to do it right now, but it is done. You can just read in these papers. And the bottom line is that with, if you do n queries, okay, you'll recover the function if it has k derivatives. So it only depends on 3 variables. It's a function of 100 variables, but really depends on 3, or let's say the other 97 are very weak. Then you'll get accuracy n, if it has k derivatives, n to the minus k over little d. It's like it was a function of only little d variables, but you pay a little bit of a cost, this log d, very much like in compressed sensing. You pay a little bit of cost in order to find these change variables. Okay, enough about that. Anisotropic analyticity. I think I'm going to, okay, I'll just tell you what the idea is. This is a pretty dominant theme in parametric PDEs. So in this setting, we're actually going to have d equal to infinity. Number of parameters, variables is infinite. We have a function that maps into a Banach space, so you can say, wow, I mean, you guys, you got hair on your chest. You're taking on a problem that nobody else would ever think about. Infinite number of variables, Banach space valued function, and you're going to do something? What the heck are you going to do? Well, the model class, the key is the model class. The model, that what you assume about f is that it's analytic as a function of z1, z2, z, so it's an analytic. If you only had a fixed number of variables, like 10, then we know the theory of analytic functions of 10 variables, right? Well, you develop a corresponding theory of analytic functions of an infinite number of variables. And then you have, when you talk about an analyticity, you say, on what region is it analytic? If you had a function of 1 variable, and I said it's analytic on a disk, right? Then you would say how nice it is depends how big this disk is, right? If you have a function that's analytic on a unit disk, radius 1, you took its power series, then you would find that this series would converge with geometric rate, right? Anywhere inside, strictly inside. Now, if I give you that it's analytic on a bigger disk, you're going to get faster convergence. So it's a nicer function. So the idea of these model classes is you're going to assume that it's analytic on a product of disks, one disk for the first variable, different disk for the second variable. These disks are going to, oh, what happened? Okay, so you're going to assume analyticity, and in each, I did something here. Yeah. So we're on a product of disks. The disk will have radius rho 1 in the first variable, rho 2 in the second variable, rho 3 in the third variable, and the rows are increasing. Getting bigger, 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 bigger. Of course, you're going to have to put some condition on how fast they get big. You're going to have to do this and that. But there is a theory. And the theory will tell you that given a function of an infinite number of variables with this kind of anisotropic analyticity. See, when you say that the rho j's are getting bigger, it means that the bigger that j is, the nicer the function is, because it's analytic on a bigger disk. And what you're going to be able to prove is that for such a function, you can capture this function to some accuracy. And how are you going to do it? You're going to compute the Taylor coefficients of this function. And now you need to know which Taylor coefficients to compute. That's one issue. And the second, of course, is how are you going to do it? If the problem were that you had to compute 30 Taylor coefficients, but they could be anywhere, then you're in a mess. It's not going to be easy to do. So we put structure. So what do? We're going to try to approximate this function, and we're going to try to approximate it by a part of the Taylor series, or let's say a polynomial. But we're going to restrict the indices, right, of the powers of z. Z to the new is like z1 to the new 1, z2 to the new 2, right? even though there's an infinite number of variables, new has only a finite number of entries that are non-zero. So each new here it has finite support. So I have to tell you what the set lambda is. And here's the key ingredient, something to write down, lower sets. We organize the indices so that they have the property that whenever nu is in the set, then any mu less than nu is also in the set. So if you put 3, 7, 4, 0, 0, 0, 0 in the set, then 2, 7, 4, 0, 0 is also in the set, and so on. If you do all this, organize with lower sets, put some conditions on the rows, how fast they go to infinity, you can begin to prove theorems, and you can say that which Taylor coefficients, we can actually tell you which Taylor coefficients you're going to have to compute a priori, so you have a theory, okay? I'm just trying to tell you examples of where high dimension we can do it. This is an example, anisotropic analyticity. The other one was only a finite number of variables were active. These are very close because in both cases you're saying the effect of some of the variables is very weak. In anisotropic analyticity, you're saying as you go further out in the variables, you've organized it in such a way that the variables with bigger index are not as important as the variables with smaller index. Okay, so there's some commonality. So that what you should draw out of this is anisotropy. Anisotropy helps you, okay? These were estimates. Okay, before I turn to neural networks. If you're interested in sparsity model classes, this was the subject started mainly for compressed sensing, so just Google compressed sensing. And actually, the fact that random queries are the best for sparse signals was known to functional analysts. So I put their names down here because when you start reading about compressed sensing, these guys, somehow they get lost. The fact that they knew what to do, where to query. The problem in compressed sensing was not where to query, random queries. Everybody knew this. The problem is how do you recover F once you have the queries, the recovery map. This is again like our two-arm thing, you know, the manifold learning. You have the A where you gather the information and then the reconstruction. The problem was with the reconstruction, and that's where Dave Donahoe and Emmanuel Candes became famous for that. Okay, tensor structures. A lot needs to be done for tensor structures. The only guys that have a good theorem is here. And why don't we know this for other tensors? Just we only know a hardcore result for rank 1 tensors. And I asked Wolfgang, I said, Wolfgang, why do we only know for rank 1 tensors? He says, look, Ron, I can do anything, but I can't do everything. I got other things I got to work on. I can't do everything. We're going to leave something for somebody else. Okay, so this is the famous quote of Wolfgang. I can do anything, but I can't do everything. You understand the distinction? He doesn't have enough time to do everything. He has to prioritize. Okay. I want to take the last, whatever I have here. Oh, I think I have about 15 minutes. To discuss a little bit deep learning, because this is, I don't know if this is going to be one of the themes of this spring school, but certainly there's a lot of activity in this field. And I guess, Geeta, you're going to talk about this, right? Yeah. Okay, so I just want to give my take a little bit to set down what I think the right questions and problems and all that is. Now, look at this. My talk is high dimension, but I'm going to talk univariate. You're going to say, well, why are you talking univariate? I mean, the reason is that we don't even know in the univariate case what the heck's going on completely. So I don't feel that we should talk about functions of 10 variables till we understand functions of one variable. So you'll probably talk about high dimension, some, anyway. Okay. So, and I'm only going to talk about what's called ReLU nets. And the ReLU function is that if you take a real number y and you apply ReLU to it, you're just taking the y if y is bigger than 0 and 0 otherwise. So it's this y plus, right? So ReLU of 1 is 1, ReLU of minus 1 is 0, right? Do you understand what the ReLU function of y is? Okay. Now I'm going to give you a graphic for what the neural nets are. So I view them as an approximation process. They're creating functions to use for purposes of approximation, just like splines or piecewise polynomials or whatever. They're just a way to approximate. Okay? Here's the picture. So I am going to create a space of functions. A space of functions, okay? And I'm going to tell you what the space of functions that I'm going to create. I input an x. I'm going to get a function of x. So I input a real number x, and it computes some functions of x here, and then goes further and goes through layers and computes functions of x, and outputs finally in the end some function of x. And I have to tell you how it does it, and what is this function of x that it outputs. So the way it does it is this first layer. So I'm giving you an example here of a neural network with width 3. There are only 3 nodes in each layer. And it has L layers. I'm interested in what does letting L get large, what does this buy you? This is what people are really concerned with. What is deep learning buy you versus I could have just stopped with 1 layer, but then this is, for ReLU, this we understand completely. So we're trying to understand what increasing L buys us. So I'm trying to keep W fixed, W to be 5, 6, 7, whatever you want. I don't care what it is, but let L get large and see what I get. So let me tell you how you compute. Each node is called the neuron. This is a node. These are nodes. I think of these nodes. To each node, I have corresponded a function of x. I'll call this function eta IL. So it's in layer L, in row position I. This is the function. So this would be row 1, 2, eta 1, 2, right? It's in layer 2. And it's in the first row position. Okay, so that's what these etas are. Now the first layer here, these functions are simply of the form ax plus b. Somewhere I must say this. Functions of this type, right? So the first node here would be a1x plus b plus, which is a function that looks like this, right? Or like that. Right? It's a piecewise linear function with 2 pieces, one piece 0, the other piece linear. Okay? So each of these nodes is such a function. And you get to decide what you want to put here, which functions you want. So if you stopped here and outputted, what would you get? You'd get a piecewise linear function, right, with three breakpoints. All right? And this is all you get. So we understand this completely. If you let W be large, but only allow 1 layer, we understand completely. This is the same as piecewise linear functions with W pieces, which we understand completely. Now the next layer here, how we get the nodes in the next layer. What we do is we take a linear combination of the functions from the previous layer, add some offsets to it, And, oh, I have the value in the wrong place. Okay, sorry. The value should be on the inside of this sum. Let's see if I do. No, I have it in the right place. Sorry. Okay. So this function here, eta IL, I'm talking about how you get these functions here. What you do is you take the previous layer, and if you want to compute the value, your function here, you take a linear combination of these, you add an offset b to it, and then you apply the value plus. That gives you that function. To apply this one, you apply a different linear combination to get this one, a different offset for each of these. So to decide how to get these functions from these functions, you apply a matrix of size w by w, and you have an offset vector of size w, and then you apply a value, and this is how you get. So the way to think of this is you start with x and you're marching on. This is supposed to be emulating somehow how the brain works, right? You're marching on and you're creating these functions, you're feeding it forward, and then finally at the very end, after you've computed these functions, this one is just a linear combination of these. Now we're interested in how, so if I let, where's my notation? This represents all the outputs, all the functions I could create in this way by choosing different matrices at every stage and different offsets. I create some functions. I'm interested in what is this class of functions and why is it so great for approximation purposes? Because people say neural networks, deep learning works really well. So it must be doing a very good job in the sense of approximation. Why is it doing better job than other classical methods of approximation? This is what I'm trying to understand. Now, let's first understand that every function here is a piecewise linear function. Every stage of this process, every one of these functions is a piecewise linear function when you do value, every time. And then when I finally take a linear combination, this is piecewise linear. So I'm just creating piecewise linear functions. And what's so great about these piecewise linear functions? So if I want to understand why this somehow, what's the advantage in this, I should compare with other ways we create piecewise linear functions. So I let sigma n, let's go back here. So I want to compare, I want to say, okay, why are these guys so good? I'm going to look at, they're piecewise linear functions, right? I look at this other space of piecewise linear functions we already talked about, which was take the interval, because I'm in one variable, I take the interval 0, 1, I divide it into n pieces, arbitrary pieces, and put a piecewise linear function down, right, on these pieces. So sigma n is this space. The space of all piecewise linear functions with n pieces. Depends on 2n parameters. This space upsilon, if I want to make a fair comparison, I'm going to take this space so that the number of parameters is like n. Okay, so I'm going to call that somewhere. Do I have upsilon n on this slide? No. Here, upsilon n. I'm going to choose the number of layers to be such that the number of parameters in this space is like n. Well, the number of parameters is like w squared times L. Every time I have the matrix, which is size w by w, is w squared parameters. The offset is w. That's smaller than w squared. the number of layers is L, I'll get W squared times L. So that's the way I'm going to compare. I have two spaces, sigma n, that space there, sigma n, depends on n parameters. And this space, which is the outputs of a neural network that involves n parameters. This neural network is fixed with W, and it has L layers. L is getting bigger. As n gets bigger, L gets bigger. W doesn't change. W is 7. Or W is 12, whatever you want. Now, there are all kinds of variants to this problem. You could let W change, let L change. You can let lots of things change. You can talk about the fact you're not going to use full matrices, only use sparse matrices. You can, but I'm looking for good rigorous theorems, so I have to put some restrictions on my generality. Okay, so I want to understand, this is supposed to be a lot better than that, sigma n, right? Why is it better? What are the hard theorems that says this is better than that? If you tell me you're creating piecewise linear functions depending on n parameters, I could say, well, I'll do this. And you say, no, 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 I don't want you to do that. I want to do this. These neural networks and all this. And I say, well, why is that better than this? Do you understand where I am so far? Okay. So I want to compare these two spaces, this one and sigma n, and see how they compare and why upsilon n is better than sigma n. Why? There are two types of results that would be impressive to me. Or, I mean, there are two ways of thinking about it. One, which is the common way people in neural nets talk about it, is they say, well, let's look at what functions appear here. Maybe all the functions that are in sigma n are already here, and I'm just adding more to it. I have a bigger pot of functions that I'm using. That would be good. That would at least explain that you're doing as well as sigma n. And then if you show a whole bunch of functions that are in upsilon n that are not in sigma n, then you've shown me that you have more power. This is called expressive power in this field. Another way you could phrase a question is you could say, okay, suppose I use upsilon n to approximate, and I look at the functions approximated with order n to the minus r, as I did before in the first lecture. I look at that class of functions. And now instead I put sigma n here and look at the same class. If my class for upsilon n is a lot bigger than sigma n, then I'm doing better because I'm not only approximating all the functions sigma n could approximate with this rate, I'm still approximating with that rate, but I have a whole bunch of new functions that I'm approximating with this rate that sigma n couldn't. So you would say, I'm doing better. Okay, so that's the kind of theorems I'm looking for. Okay, and I'm going to tell you some results that we did with these people. Okay, first question is sigma n contained in here? That is, if I look at the outputs of this neural net, am I all the guys that were in sigma n? Because I know I'm getting piecewise linear guys. So is every guy that I would normally get this way already gotten with this way, with a neural net? And the answer is yes. You have to take, go out enough layers, comparable in number of parameters to n, but every guy that's in sigma n is contained in here with C with a fixed constant like 12. This is not the best constant by any means. We know that it's not the best. So don't write a paper that says I got C equal 8. But if you can write a paper that says I have C equal to 2 and nobody can do better, write it. Okay? All right. So that's one thing. Now the second thing is I want to say, are there a lot of functions that are in upsilon n that aren't in sigma n? Well, this is pretty well studied. I know Gita studies this and other people. And let me just say a little bit about this. The reason that it turns out that there are a lot of functions that are in here that aren't in here. And the reason is a property that upsilon n has that sigma n doesn't have. And the property is composition. If you take two functions, f and g, their composition is you apply first g, then f. Remember Hilbert's 13th problem that I was talking about? Okay, this is the composition. Now, if I take two functions, one from sigma n, another from sigma upsilon n, another from upsilon m, and I compose them, then you can almost see that the composition can be gotten by n plus m, a neural network of n plus m. See, think of this as your neural network that inputted x, outputted t, and now follow it with the neural network, right? Just take that output and then input it into the neural network for s, right? This given x outputs s of x. Given t of x, it will output s of t of x. So it outputs the composition. So neural nets have the property that if you can produce an s in upsilon n and a t in upsilon m, then you can create a neural network that produces the composition of s and t. And the number of parameters you need is just n plus m. This is important. You just add the number of parameters. If I ask to do this with sigma n, what happens? If I have a piecewise linear function with n pieces, one with m pieces, and then I look at the composition, how many pieces will it have? Generally n times m. So that means I would need n times m for that, but I only need n plus m for here. Okay? So you can compose cheaply. You can do the composition cheaply. Both of these classes of spaces, sigma n and upsilon n, can do addition cheaply. They can add two functions cheaply. If you have a function in upsilon n, another function in upsilon m, you add them together, you get it in upsilon n plus m. Okay? So these are the two operations. But the one that upsilon n, the neural networks, has that piecewise linear doesn't have is this composition. Okay, what does that buy you? Well, it buys you a very powerful apparatus. Let me give you the simplest example. Suppose I take the hat function. Okay, this function is both in a neural network of very small size, 2, like that, anyway. And it's also in sigma with one breakpoint in the middle. 3 breakpoints, one in the middle. Okay, now I compose this function. If I compose this function with itself, I apply h to h. I take h of x. These functions map 0, 1 into 0, 1, so I can compose them. If I compose it, let's say 3 times, h cubed, this circle thing means compose. 3 times, h of h, I get this guy, sawtooth guy, right? How many goes up and down? How many? Look at how many times it goes up and down. If I put h4, it'll go up and down another 4 times. I do h5, it'll go up and down and I apply 10, it'll go up and down 1,000 times, thousands of times up and down. Now, if I want to represent this function with sigma n, with this space, I would need to put down thousands of breakpoints, right? It's got a lot of pieces. This counts, every piece counts here. This, I can do it with very few parameters. If I put down the piecewise linear guy, this is called a sawtooth function, with 2 to the 10 up and downs, I can represent it with 10 parameters, roughly 10 parameters. That's the power of these neural networks, is this composition power. Okay, this has a lot of generalizations. I mentioned one. If you take a function in sigma k, S, it's a piecewise linear guy, right? We know everything, but it may have many pieces. This is the thing you need to understand, that sigma 7 could have 2 to the 7 pieces. I mean, up and down, but not every 2 to the 7, right? Not every function with 2 to the 7 pieces is there. It can't be. Only some of them. But if you start with one guy, it's an epsilon k. And now, if I want to replicate this guy, I can replicate it I can partition 0, 1 into any, let's say I partition it into 5, 1, 2, 3, 4, 5 intervals. And I have this S. I can put S here, whatever S is, and replicate it here. And I can scale it. So sigma, the epsilon n, can make copies of any given function. You give me a function that's in here, I can create this function, which is to take the interval 0, 1, divide it into pieces, and put a copy of S on each piece. And even I can scale it. That gives me the power of being able to construct a lot of fractal-like or self-similar functions. Functions that look like the same everywhere. But I can scale it because I can make one interval real small, the other interval real big, and then I can magnify the amplitude of this as I wish. So that's a powerful thing. These are called patterns, and the cost of creating the pattern, this is the important thing. It costs you the number of intervals, 6, okay, times the number of intervals. And it cost you k, but you needed k anyway to get here. So this is a very modest cost. If you try to do this kind of a thing with piecewise linear, what would it cost you? Well, it cost you k right? Every piece would cost you k. So it would be k times m. So the comparison again is between k plus m and k times m. Just like in tensors, right? I mean, you're linear in the parameters as you increase your complexity rather than multiplicative. Okay. Oh, you can create zillions of functions and examples and frames and bases and all that with these constructions. But I don't have time to do all that. Now, let me tell you a general principle. So that was the idea of why epsilon n is better than sigma n from the point of view of expressivity, that is the functions in the class. But now you can say, well, yeah, but what about approximation power? Why are they better in approximation? And now I'm going to answer that question. So here's the general principle. If I take some functions in epsilon k, and let me normalize them to have norm 1. And then I write down a function that's an infinite sum of these functions. So think of, k equal 1, you got to wiggle up and down a little bit. K equal 2, a lot more wiggles up and down. K equal 3, wow, lots of wiggles up. And I keep doing this. These are my phi k's. Multiply them by constants alpha k. I take the sum and I get a function. Okay? Now, if I make the alpha k, so I have to make this so that the series converges and that I can chop the series, right? So I do this in such a way that the coefficients satisfy this property that the tail behaves like n to the minus 2r. Then when I chop it at n, if I chop this series at n, I will have a guy in epsilon n squared, right? Because remember, if you add guys, you just add so you're adding 1 to 2 to up to n, you get n squared, okay? So any one of these functions will be in AR. So you can create a whole bunch of functions. in this way, by just simply adding. You can think of these as atoms. You know, we used to do atomic spaces. These are your atoms. You add your atoms up, you get a function in AR by putting some restriction on the coefficients of the atoms in terms of the growth. Okay, so you get a whole bunch of functions. Now, you know, it's sort of impossible to describe all the functions this way because you could take any phi k and you can take any alpha k and you take the sum and you get a function. But let me mention a couple functions. Look at the Tagaki function. This is the function studied in dynamical systems. Did you know? You don't know this function. This is studied in control theory and dynamical systems. Now, this function, which is to take that hat function that I had, right, the sawtooth guy, and I put coefficients 2 to the minus k. Yeah, 2 to the minus k in front. Then this function here will be approximated by elements of upsilon n to exponential accuracy. If I take upsilon n, it will approximate this function to accuracy 2 to the minus n. Right? You can see that. Because you just chopped the series and the tail is 2 to the minus n. And I've used how many terms? I've used n terms only, right? This guy is in upsilon k. So, I mean, I'm going to get exponential accuracy. And yet this function is nowhere differentiable. It's a lousy function from any point of view. I mean, it's lip1 function. It barely made lip1, but it has no derivative at any point. So it's a lousy function, and yet I'm capturing it with infinite accuracy, with exponential accuracy. Okay? So it's in every one of these classes. In fact, even better, I mean, it's in exponential accuracy class. You can create a whole bunch of functions from iterated function system, fractals, refinement equations. You can take whatever starting point you want, and you can create a bunch of functions that are in upsilon n and can be approximated. Sums of these can be approximated with high accuracy, where these guys couldn't do it hardly anything in terms of approximation. Terrible job. Okay? And at the other end of the spectrum, you can approximate all the analytic functions well. I mean, this is what Weinen, his paper with whoever that was using. The fact that with these neural networks, you can approximate the functions x squared, x cubed, x fourth, all with exponential accuracy. And I think you do things like where you approximate your shearlets with exponential accuracy. There are a whole bunch of functions that can be approximated with exponential accuracy. The fact I can do these with exponential accuracy, I can approximate any analytic function with exponential accuracy. So it's very rare that you have such a powerful approximation system that you can do all the spectral rate guys and you can do all the polynomial rate guys and all the fractals and all the refinable and every function. So it's a very powerful tool, but not clearly described yet in terms of exactly what it can do. Here's a little bit. I'm almost done if you're getting tired. But another little surprise here. If you take any function in lip1, you can approximate this function to accuracy 1 over n times log n in the denominator. Now, this should make you shiver a little bit if you're in approximation theory. Because you say, I want to approximate a lip1 function. The best I'm going to do with 1 over n. Where the hell does this log n come from? You should worry about this. But it's there. And it's true. And it uses this self-similarity business. I won't go into the detail. But it should make you worry, and so I say here, what is going on? How can you do this? Because this seems to defy my entropy bounds. The entropy of lip1 we know, and the entropy would tell me I can't do this. So what's going on? What's going on is that if you look at this approximation by these neural networks as manifold learning, where you're given F, you determine the parameters, that's the matrices and the offsets, and then once you have the parameters, you can determine the output. So you have these two maps, A and M. They're discontinuous. The A is discontinuous. You can have F's very close, but the A's are going to be different. In fact, they must be, if you're going to achieve this accuracy, they must be discontinuous. Okay? So my point is that you better be very cautious about stability of your algorithms. And if you're claiming results on approximation, you better not just claim that you can get a certain rate of approximation, you better show that you can implement it numerically with a guaranteed stability. Because otherwise you're going to get in a situation where two functions are very close, the parameters are completely different, and numerically when you try to implement this, this will be a mess because any imprecision in your computation will show up in your results. Okay, do I have anything more to say? This is it. However, I had one verbal thing to say. And okay, I talked about neural networks, one univariate functions. I think if we go just, you know, I would say to a student, boy, don't do that when I'm going to tell you. That is, let's look in two dimensions. Because I would say to somebody, you don't do one, and then you do two, then you do three. Look, if you go above one, you should do it all, right? K dimensions, D dimensions. But if we go to two dimensions, it would be interesting to understand what are the functions outputted by these neural networks in two dimensions. They with ReLU. They correspond to some partitioning of the domain into piecewise polynomials. And I guess, you know, they could be a lot of pieces on a given, I mean, I don't know what it looks like, but I would say that's the next step. Okay, thanks, and I'm sorry if I took too much of your time. Okay. Thank you.
Thank you very
Thank
much.
you.
So, are there any questions, comments?
Well, maybe they didn't follow. So you can ask a dumb question. It's okay. I think it helps me if you ask. No?
Yes. The first dumb question.
Okay.
So when you were talking about entropy, you briefly touched upon the probabilistic world. Everything here was deterministic.
Yeah.
So if the check of entropy can be somehow relaxed if you're happy with some probabilistic recovery guarantee.
So, that's a good, if I understand your question, it's a good question that concerns us in numerical analysis. And here is the question. In numerical analysis, we have algorithms and we say, what are your guarantees that you've recovered what you want to recover, what you want to compute to a certain accuracy? You want to compute how much cement to put in the bridge. And you did all this calculation, you came up with a number. We call this uncertainty quantification. Tell me how certain you are that this is the right number. And in numerical analysis, okay, we ask for deterministic certainty. That is, we ask that when you're done, this is the answer. Period. No wiggle room left. But you could ask, you could ask for a statement that says this is the answer with high probability. With probability of failure 10 to the minus 10. That should open the door to doing more numerics, right? Getting better accuracy for fewer computations because I don't require you to guarantee, right, this accuracy with certainty. I will accept it with some high probability. This is a general question in numerical analysis, and I don't think it's been well studied. But there is this flavor here, somehow. I don't know the precise description of it. You know, I haven't thought enough about it to put down a term. But was that your question or not?
Yeah, it's kind of an open one.
Maybe it wasn't your
thoughts.
question, but you'll take it, right? Okay, okay, yeah, oh, okay, that sounds good, I'll take that question. Yeah. Okay.
So if there's no
Before I
urgent
retire.
immediate one, we will have time to chat.